Early last year, Mozilla announced that we had reached the point on the internet where half of the page loads in their browser were occurring over HTTPS. Earlier this year, HTTPS adoption has grown even more, and Chrome announced that over 78% of the connections in the Chrome browser were happening over HTTPS. This is a great improvement, a great way forward in protecting privacy of online users everywhere. And TLS comes from the Internet Engineering Task Force, and it started as an idea all the way back with Netscape in 1995, kind of solidified into a better standard around 1998, and it was updated again in 2006 and again in 2008. And we've been running with that version from 2008 for about the past 6 or 7 years. And there hadn't been a significant advance in the actual protocol until very recently. So now, 2008 to 2018, TLS is changing again. But before we get to talking about all the new stuff that's happening with TLS, we need to go back and understand a little bit about what happened in the past and how the handshakes before 1.3 were handled. So the names change, but pretty much the handshake remains the same throughout these older versions of TLS. The handshake is the most important part of the protocol. It's what sets up the security for everything that happens afterwards, which is the encryption of your data and securing of all your transactions. So in a handshake, you agree on some main things. You have a certificate that you agree on. Either the client or the server both use a certificate to authenticate one side to the other side. You also have the authentication algorithm. So what type of algorithm are you going to use this certificate with to prove the identity to the other side? What encryption algorithm are you going to use? Which cipher? So we'll go over a whole bunch of different ciphers that are useful in TLS. And then finally, how do you get the encryption key that you're going to use to encrypt the data using that particular cipher that you've chosen on? And I'll also say all these slides are available online. If you go to the LASCON schedule website, you can click a link and download those so you can get some better resolution copies. So let's walk through each of these little steps in TLS 1.2. So here I made this little chart to help show an example of a handshake in TLS 1.2. You start out at the top, it flows down to the bottom. Once you get past this last message, that's where you're encrypting all your application data. So another thing to note, I'll have several of this style templates throughout the slides. The red letters, so you can see here in the very bottom of each side, the red means encrypted. That'll get important as we go on. So for authenticating the algorithms, so you have a whole bunch of different ways to authenticate. You use the certificates and the connections to do that. Both the client and the server, as I mentioned, can use these certificates. You can use the RSA algorithm, which was developed a long time ago. You can use elliptic curve, Diffie-Hellman, or digital signature algorithm to do the authentication here. RSA is very widely used, widely supported. A whole bunch of the certificates on the web today are using RSA. With the elliptic curve, those are gaining popularity at a very rapid pace thanks to a large content delivery network giving out free elliptic curve certificates to everybody that signs up with them. And so now a lot of the traffic over the internet has started to move towards that elliptic curve certificate. And then you have this option of a pre-shared key, the PSK option. That's where you can get, if a server administrator can configure both sides of the connection, they can import a large cryptographically random key onto both sides, and they can use that to establish the communication between the 2 points. And what that allows you to do is to have that handshake be a whole lot lighter. You have to transmit a lot less data whenever you're using the PSK algorithm. And then there's this crazy one over here, none. That's right. You can do TLS. You don't have to use certificates. You can just not care who you're encrypting to. You can encrypt and not validate at all who you're sending the data to.
I'm just curious about that very interesting punctuation, if that's actually a single symbol.
Yes, that is a symbol. That's an interrobang. It's a question mark exclamation point combined. Yes, it's on Wikipedia. So if you don't believe me, you can check there. So the none algorithm is kind of an oddity. It's mainly used internal to data centers. So if people are caring about the integrity of the data not getting changed, they'll use an encryption algorithm to make sure that whenever it gets to the other side of the connection, if it's still decrypted, they consider it still valid and good. But they're not as concerned about authenticating exactly where it came from, because in their risk profile, that risk is a lot lower. Now, on the web PKI, it's a whole different story, because there's a lot of other things in between the points that are transmitting that data. And it's a lot harder to have that trust in the network. So on to the ciphers. There's a whole lot more ciphers than I've listed here, but these are some of the ones that have been used predominantly over the past few years. So you have 2 flavors of AES, the old 1980s standby triple des, and a new one called Cha-Cha 20. So this one, yeah, it's named after the dance move Cha-Cha. I'm not sure if anybody can demonstrate that for us, but no, okay. I can't either, I'm sorry. But again, you have this really cool one called None. That's right, you can do TLS and you don't even have to encrypt anything. You can do TLS without certs, you can do TLS without encryption, and it's still part of the valid protocol. It's not safe to do it that way because the data is transmitted completely in the clear. Luckily, none of the browsers support that option. So if you notice, AES is up there 2 times. One is a chaining block cipher mode, and the other is the GCM, the Galois counter mode. So that's a newer implementation of the way to string together blocks of AES encrypted data. So what that allows you to do is have your data authenticated as well as encrypted. So there's a couple of attacks out there to where you can modify the data in transit, and then based off of how the decryption happens on the other end, it will send back error messages at certain different timings along the encryption process. And you can use those timing attacks to find out some stuff about the data that the other side is trying to decrypt. So with the GCM mode, it puts that authenticated piece on top of the data packet, and then allows you to validate that the encrypted packet that you received is the right piece of data to try to decrypt. And so it squashes those attacks and makes it safer to use. Cha-Cha 20 is also one of those authenticated encryption ciphers. And as a class, a family of ciphers, these are known as AEAD, authenticated encryption and associated data. And Adam Langley, one of Google's cryptographers, reminds us that everything at the time that's not TLS 1.2 with AEAD mode is cryptographically broken. So that triple des, that AES CBC, cryptographically, not maybe practically, but it's cryptographically broken. So let's look at some of the ciphers that you can choose to use with these early versions of TLS, from 1.0 all the way up to 1.2. There's just a few of them. But wait, there's more. How do we pick the right ones? How do we know? This is ridiculous. There's way too many. It's up to server operators, the people that are there configuring the servers, as well as the application and device manufacturers, to build and support and to choose the right ones, to know which ones of these are safe to use. And if you don't, there's a great tool out there that's free for anybody to use called SSL Labs. And you can plug in the name of your server, it'll go interrogate it, check all of these, and see which ones you support, and then give you back a report and a letter grade so you can see if you can improve your score at all to be more secure. The next piece of the puzzle is how do we get the key across to both sides? Both sides have to agree on the same key, but we can't just yell it out in the clear because then everybody will know it. So we have to transmit it or agree upon it somehow. And the first method is the static key exchange. And this is a way to use, pretty much is always using RSA. So you take the public key from the certificate and you encrypt a private piece of data with that. And the only person that can decrypt it is the one that has that certificate's private key, which should only be the server on the other end of the connection. And this has great useful properties for debugging. You can take that private key, you can throw it in Wireshark, you can watch all of your connections going out to that server, and then you can decrypt them as long as you have that private key. So if it's your server, that's great. You can decrypt any of the connections going to that server, whether or not they're yours, because you have that server's private key, which is why you need to be careful where you put that. However, this also means that if there's maybe some big internet-facing bug that allows somebody to download your private key off of the server in a couple chunks of memory at a time, like Heartbleed, then anybody that does that and grabs the private key off your server that's also been recording all the traffic to your server over the past 1 or 2 years, they can also decrypt all of the traffic that's gone to your server. It's not current best practice, but the static key exchange is still used a whole lot day to day. And industry best practice, though, is to move off of that and onto the second method, the ephemeral key exchange. And sometimes you've heard this called perfect secrecy or forward secrecy. And it's the idea that every connection uses a different set of keys to agree on the encryption key. So you use some type of asymmetric cryptography to come up with that AES key that you're going to use. There's 2 main algorithms that are used to do this, Diffie-Hellman and elliptic curves. So with the Diffie-Hellman, that method is really slow and the keys are really big. And the other problem is you can't negotiate the key size. So there was a bug where a while back where you could force somebody into using a really small key size for the Diffie-Hellman key agreement and basically transport them back to the 1990s crippled cryptography area where it's fairly easy to just decrypt any of those connections. So the Diffie-Hellman's being moved off of, so a lot of the browsers are pulling support for it and moving to just using elliptic curves for the key exchange. Elliptic curves, a good thing about those, it's faster. The key size to strength ratio is way, way smaller. So, and they're negotiable. So you can choose, you can send as a client which curves you support, and the server can look at that big list of curves and say, oh yeah, I support that one, let's do that. So now, finally get to TLS 1.3. So this was released and published in August of this year. So it's out there, it's ready to use. You can go download it. It's a whole lot of pages long. And just a cool thing about the numbers, so TLS 1.3 is RFC 8446. If you'll notice, all of the TLS series ends in 46. I don't know what 46 means, but this was just something cute that they thought they could do. 4 and 6. So let's look at the handshake. So here's the comparison between TLS 1.2 and 1.3. So you can see there's less arrows in 1.3, which is good because that means it's faster. There's less trips back and forth across the internet. And there's more red letters. That's another good thing. More things are encrypted in this. So it's protecting more of that potentially sensitive information that you're transmitting over the wide internet. And we'll come back to another comparison of this later, so you don't have to memorize it now. In the connection handshake, it's the same things that you need to agree on for 1.2. They're just done in a slightly different order in a little bit of a different way. So you still have to get your certificate that you're going to authenticate the other side with. You still need your authentication algorithm that you're going to use alongside that certificate, which cipher you're going to use, and how to get that key for that cipher back and forth. RSA still supported. All your existing certificates work. So the way it's designed, it's decoupled the certificate from the protocol. So all the certs that you were using from TLS 1, all 1.2, you can use the same ones in 1.3, no problem. The difference is, with RSA, there's a new algorithm that's used to do that proof that the server is who they say they are. This new algorithm is called PSS. And the old algorithm is PKCS1 version 1.5. It had some issues with it. PSS is a lot better. It adds robustness to the algorithm proof. So it adds in randomness and a way to strip out that randomness whenever you're doing the verification. So it increases the robustness of that proof in the handshake. You can use your elliptic curve certs too. That's still good. And yes, Steve?
Does PSS replace PKCS?
So PSS in RSA replaces in the handshake message here the PKCS 1.5 style signature. So it's not replacing the entire PKCS series, it's just replacing the signature algorithm from that series that's used in this. And the other part is the proof message where the server signs the little chunk of data with its private key. That message is now done over the entire handshake instead of just bits and pieces of the handshake that was used in TLS 1.2 and prior versions. So it makes that part of the proof that the server is who they say they are a lot more secure. Now onto the ciphers, there's a lot less. There's no none. There's no none back here either. So they've taken off that ability. These are just AEA mode ciphers. So now we're only using the cryptographically secure ciphers with TLS 1.3. And we've thrown out all of the older, weaker ones. AES is one of the mandatory to implement cipher suites. So in the RFC, there's two kind of categories of things to do. There's mandatory, which says I abide by this standard, and because I do that, I always will support this. And then there's a should. So the Cha-Cha 20 is under the should methodology. So anything that's wishing to implement the standard, they really ought to implement Cha-Cha 20. But because you always have AES, that's going to be there as a backup, just in case you don't have both. There's different reasons you would want to use Cha-Cha 20 versus AES. If you have a processor that doesn't have a special AES chip inside of it or next to it, it's probably going to be a lot faster to use Cha-Cha 20. It was built for speed. And then Intel built a special coprocessor that implements AES that takes a lot of, there's a time memory trade-off deep in the internals of AES. And so they've taken that time memory trade-off and built a chip that has all the memory part in it. So that makes it a lot faster on laptops, for instance. But on some of the, especially older phones, they don't have all that AES coprocessing. So whenever older Android phones would talk up to Google servers, they say, hey, can we do Cha-Cha 20? And Google would say, sure, that'll be faster for you, let's do that. So the ciphers, no, I'm just kidding, that's the old slide. They pared them way down. There's just 5 with TLS 1.3. So this is straight out of the TLS 1.3 spec and all its ASCII art glory. Just these 5 ciphers. So you have AES, there's actually 2 modes, CCM and GCM. CCM is a counter mode of AES, but it still has that authenticated piece in there with it. So it's still safe to use. All of them are the AEAD mode. It's not to say other people aren't trying to add new ones. There was, shortly after this RFC was published, somebody came back and said, hey, I have a great idea, guys. Let's add in the none cipher. And the reaction was similar to that, just kind of laughed them off stage. Hopefully it stays that way, I'm not sure though. Onto the key exchange. The only type of key exchange you can do is ephemeral. This is probably the most controversial change between the older versions of TLS and the current version. The reason is a lot of the larger enterprises and banks were banking on that static key exchange to still be there. The reason is they use it inside of their networking devices like web application firewalls or intrusion detection systems to crack open TLS on their network edge and inspect the traffic before they pass it back to their web servers. So with TLS 1.3, they can still do that. They just can't use the RSA method to do that. They have to do it in a different way. And that might end up having to re-architect some of their software and the way they've designed their networking infrastructure in order to do that. There's 2 different algorithms that you can use with the ephemeral key exchange here. There's the elliptic curve, which is the same methodology used in the older ones. But now instead of Diffie-Hellman, there's a new version of Diffie-Hellman that's safer and is able to be negotiated, so you don't run into that interoperability problem that you ran into with just the regular Diffie-Hellman in the older protocols. So this is the finite field ephemeral Diffie-Hellman. And it's still slow, and so you probably still just want to use elliptic curves. I don't know of any browsers that are actually implementing this. I think some of the crypto libraries like OpenSSL, they still are, just so that they can have it. But it's there just in case anybody needs it as a fallback from the elliptic curves. There's another mode for TLS 1.3 called zero round trip time. And this allows you to take it and speed up the delivery of your request to the server significantly, all the way in the very first message that you send. So the very first time you connect to the server on a new TLS connection, you're already saying, hey, give me the web page over here. And then in the very next message back from the server, it says, all right, here's all the stuff you need to set up the TLS connection, plus here's the results from your question. Here's that web page. So that sped up the data getting back to the client massively, especially if you're on a high latency connection like satellite or in the middle of the ocean. There's a couple of problems with this though. That very first message isn't forward secure. It's encrypted with a semi-static secret that's stored on the server. And so you need to be careful about what you send in that first message. Even more importantly, it's prone to replay attacks. So one of the people that was working on the TLS 1.3 spec discovered this problem in another protocol that Google was developing that was very similar to this, where you could take that very first message that the client sends, and let's say it was destined for a cluster of servers or a content delivery network or something. So they take that message, hold on to it, and then spray it across the entire content delivery network. So now your request, whatever it was, is now sent to all of their servers and processed. It might not be a big deal if you're just asking for the homepage. But what if you were buying stocks or cyber tokens or groceries? All of a sudden now you have 50 gallons of milk ending up at your house instead of one. There was a great talk at DEF CON this past year about this. So they did a whole 40-minute talk about it. So I can't go into all that same detail here, but they have examples and demonstrations that they built tools to actually pull off this attack on the version of TLS 1.3. And so what you need to know about this is that whenever you're setting up an application to use TLS 1.3, you need to be really explicit and careful about when you use the zero round trip time. And a lot of the content delivery networks that are planning on implementing this are planning on putting in safeguards. So I know Cloudflare has the option to use this, but you can also turn it off if you think it'll be dangerous for your application. Another CDN was talking about possibly just only having the zero round trip time for certain directories or certain URLs that people are requesting. So it really depends on your use case, but for a lot of URLs probably on your website, this could be a really big help and help speed up the connections of clients coming to you. So let's race the different versions. All right. So here are the things that the handshake agrees on. You got your cert, your cipher, encryption key, and then your HTTP request and your response. So let's look at the plain default regular old versions of TLS from 1.2 and earlier. So the client sends out a message. Nobody's gotten enough information to agree on anything yet. The server sends back one, and now you have enough to know what cipher you're doing and what search you're using. When the client sends back its next message, the server and the client both know what the encryption key could be. They tell the client that, and then the client says, okay, well, here's the request, and the server says, here's your response. It's a lot of back and forth. In 2016, the IETF looked at that lot of traffic going back and forth and said, hey, I think we can probably speed this up just based off of how the internet works. We think we can squish some of these messages together. So they came up with this idea called false start. And it's still pretty new, but a lot of the browsers support it, at least the ones that are considered modern. So Edge, Chrome, Firefox, just not IE, basically. And other TLS clients on the internet might not support it. So with false start, it looks the same up front. Send your request, get the response. Now you know the cipher and the cert. But when the client sends its next message, it'll send the information to get the encryption key, and it'll also tack onto that its first application request. And then the next message back, you can get the response. So that's a pretty significant speed up. It saves a whole round trip of time across the internet. And with 1.3, you get a fairly similar thing. In the first message, the client, after the first message comes back, the client has enough information to know the algorithm and the cipher, but it also knows the encryption key because it sends, in the very first message, information to the server about the key exchange method. And then you can continue on and do your HTTP request and response and get that information back. With 0RTT, though, on the very first message the client sends, you get your cert, your cipher, encryption key, and you can also throw in that first HTTP request. And then the very next message you get back from the server, you have your response immediately. So let's look at that in trans-Pacific round trip time. I chose trans-Pacific because it's a round number, and Atlantic was some weird number. So with false start, you get 200 milliseconds. And then, false start is 400. The zero round trip time is 200 versus the about 600 if you do the old style of 1.2. So that's a pretty significant speed up there. So let's go back and look at this handshake again one more time. So you notice the red, the cert is verified, is encrypted. The HTTP data is encrypted, but I didn't tell you what else comes across in that client hello. You see, in order for the server to select the right certificate, it has to know what service you're trying to talk to. And built into TLS 1.3 is a mandatory field called server name indication. And it's a way for the client to tell the server, hey, I'm trying to talk to Google right now. Can you give me a cert for Google? And that's important because with people still trying to host things on IPv4, if you're trying to stand up a network for a whole bunch of servers or a whole bunch of hosts, in the old way of doing things, you had to have a different IP address per customer. So one IP address equaled one cert. But with the server name indication, you can have one IP address and how many ever certs you can handle. But that's because of the server name indication. So the client tells the server, hey, give me this cert. Give me the cert for Google on this first initial message. And then the server can look at that and say, okay, they want the cert for Google. It goes and rummages around in its cert backpack and then throws the cert to Google back down to the client. Before, it didn't know what service the client was trying to talk to until it had already gotten to the very bottom of that. You have to wait till the HTTP data and pull that out of the host header that gets sent. So in order to facilitate this, lots of hosting on a single IP, they put in SNI. The problem is, it's not encrypted. So if you're trying to preserve the privacy of the connections that are going across to these servers, you really should be encrypting everything in order to help preserve that privacy. So if you're somebody monitoring a network and you don't want people connecting to like the FBI tips hotline or something like that, you can block the traffic that says, hey, I'm trying to get to the FBI tips hotline. And then that traffic will just not be able to go, and then whatever thing you're trying to stop will not get through. But they're solving for that too. So there is a draft in the process in the IETF that's just entered in. It's called the last call in the working group. And that means, hey, we think we're all done. What does everybody else think? And the support for it has actually already been beta tested out in Cloudflare and on Firefox. So what that allows you to do is encrypt that server name before you send it over to the server. And then the server has the information already to be able to decrypt that and then respond with the appropriate cert back to the client. And it uses the DNS lookups to do that. So in the DNS lookup, whenever you're asking for the server IP address, you also say, oh, and by the way, give me the encrypted SNI key. And so that response from the DNS server will send you back the key as well as the IP address that you need to send to. And so you can encrypt using that key that gets sent back over DNS, the server name. And that's about the last piece of information in there that you would want to encrypt. Everything else is just random values that are calculated on the fly, and so they're of no real value, and they're random each time over the connections. So that server name is the last piece of information that's not private. Yeah. So the question was about SAN certs or subject alternative names. That's where you can put a whole bunch of names into one cert and then configure that on the server. I'm not familiar with the problem that Google had with configuring SANs, but
I guess if you didn't have one,
if you didn't have a SAN, then Chrome would give you an error message. Yeah, so this is different than that. So there was a lot of tools on the internet that people were using to, like Fiddler, for example, didn't put the name of the server into a special place in the cert. And if the name wasn't in that particular part of the certificate, then Chrome said, well, I can't validate this. The reason was the common name area of the certificate where it was going to get that information has been deprecated for 10 years. And Google finally said, okay, we've had enough. We're going to finally actually deprecate this. And so they killed support for it. But that's a different thing than this. So with the subject alternative names, you can still do that same thing and have a whole bunch of different applications on one host. And you just have all the different certificate names in the SANs of a cert. The problem with that is if you're in a CDN and maybe somebody transfers that domain away to a different CDN, and they say, okay, we're not using that CDN anymore, and there's a whole bunch of companies listed in that cert. And they go to their certificate authority and say, I didn't authorize that cert to be used over there by them. Please revoke it. Well, that CA has to revoke that cert within 24 hours. And so now all the other companies listed in that certificate are now offline until they can get a new cert. So that's part of a problem with the web PKI and the revocation process and cert renewal process. A way to mitigate that is to have a whole bunch of certs hosted individually and have each of those companies get their own cert. But in order to do that, you have to have this server name indication supported on the client and the server. So the question is about, is there something that's special that needs to be configured in the DNS to have that piece of data ready to go to the clients whenever they're asking for it? Yes. So you have to be able to support the ES&I in the DNS and then configure the support between your server and that DNS to be able to know what that secret is so that it can be supplied back to the clients whenever they're asking for it. So you might need maybe a tighter coupling than a lot of people have between the DNS and the TLS applications. Yes? Mutual authentication is not mandatory in TLS 1.3. It's still possible, and you can still do it, but you do not have to, which is good because a lot of our phones and laptops, we don't have private keys or certificates sitting around on here. And most of the servers online, they don't really care from a certificate perspective who the clients are coming towards them. They'll use different methods for authentication like OAuth or SAML or just regular username and password type of thing. So Senator Ron Wyden just sent a letter on Wednesday of this week asking I think the Secretary of the Department of Homeland Security to make ES&I, the encrypted server name indication, a requirement for any cloud providers that federal agencies are trying to purchase. So if that happens, then that should bring support for the encrypted S&I value to a lot of cloud providers. So as far as rolling out support for TLS 1.3, Facebook, as far back as early August, so basically as soon as this RFC was published, was already 50% TLS 1.3 traffic. The only stuff that wasn't going TLS 1.3 were old applications that people hadn't updated yet from their various app stores, and browsers that hadn't rolled out support for TLS 1.3 yet. Cloudflare in mid-September was already at 20%. And that's because they don't control their clients. So Facebook, it controls their app, so they built in TLS 1.3 support into their app. And I imagine that's how a lot of Facebook traffic gets managed. But for Cloudflare, the only reason it's so low back in September is because the browsers hadn't rolled out support for it yet. I just don't have the updated numbers for them. So 1.3 is already supported in the latest version of OpenSSL, 1.1.1, that's been released. So support for 1.3 will be rolling out into anything that pulls in the OpenSSL libraries pretty soon. There are other CDNs besides Cloudflare that are rolling out support. Chrome released version 70 10 days ago, and that included support for TLS 1.3 by default. Firefox has had it since early August. And I found out that Nginx supports it as a version 1.15.3. So it's pretty much all ready to go. Any other questions for me?
What are the difficulties of moving to 1.3?
So with 1.3, the difficulties are going to be predominantly things like making sure you upgrade all of your applications and cryptographic libraries. So a lot of servers or applications will build in specific cryptographic libraries into them, and you have to wait for like Tomcat to release a new version of Java that includes 1.3, and then you have to wait for your application to include that new version of Tomcat in the app before you can put it on the server. So it'll be that, plus some of the things that I mentioned around the way that big enterprises are using 1.3, or using the RSA key exchange and relying upon that for their security tools. That's going to be part of an issue going forward. They're going to have to rethink the way that they use their network devices.
If you go to the multi-domain solution with a single IP address, how does a 1.2 negotiate that?
So 1.2 also includes support for SNI, and you can still do the exact same thing that I talked about doing here with 1.3. The difference between 1.2 and 1.3 is in 1.2, it's not a mandatory feature. In 1.3, it's one of the mandatory extension implementations. So a lot of things have support for encrypted not for encrypted SNI, for regular SNI, but not everything. So if you do enforce it on your server, you're going to run into a problem that some things aren't going to be able to connect to you. But if your target audience is just modern browsers or the latest version of Chrome, Firefox, IE, and Edge, you're going to be fine.
Hey, thanks for the presentation. Curious, you mentioned about how Senator proposed, pushing this for more federal adoption. What about other industry and other business types where, like PCI, for example, what's kind of the push there and some of the additional, I guess, driving motivations for getting towards 1.3?
So I guess I'll preference this by saying I'm not a QSA, so I can't speak for everything that PCI is doing, but so far PCI has just said that you shouldn't do early TLS. And there's been different interpretations of that, ranging from TLS 1.0 and before, or TLS 1.1 and before, depending on who you get for your QSA. They've made no mention so far, at least publicly, on what to do driving forward into TLS 1.3 or encrypted SNI. Encrypted SNI is not even a full standard yet, so I'd give them at least till next year or maybe year after to say anything about that.